And whenever you are ready, you can start the talk.
Oh. Okay, thank you very much. I'm very thankful to the organizers for allowing me to speak at your esteemed conference. So this is the title of my talk. I'm going to discuss Patislam model building from intersecting D6 brains. And this is a general outline. So basically, I'm choosing the T6 over Z2 times Z2 orientifold, which is a product of 3 2 tori with the orbifold group Z2 times Z2 having the two generators theta and omega associated with the twist vectors half, minus half, and 0, such that their action on the complex coordinates is given by the following equations. So theta changes the Z1 and Z2 coordinates by a negative, and omega changes Z2 and Z3 by a negative. Orientifold projection is the gauged omega R symmetry, where omega is a world-sheet parity that interchanges the left and right moving sectors of a closed string and swaps the two ends of an open string as the following. And R acts as the complex conjugation on the coordinates Zi. So this results in 4 different kinds of O6 planes corresponding to omega R theta, omega R omega, and omega R theta omega respectively. These orientifold projections are only consistent with either the rectangular or the tilted complex structures of the factorized 2 tori. Let the wrapping numbers of the rectangular and the tilted tori are given by n basis vector ai plus mi basis vector bi and ni basis vector a prime plus m basis vector bi respectively. Then the a prime is related to a by a shift of half times b. So a generic one cycle n comma l satisfies l equal to m for the rectangular case and l equal to 2m tilde, which is equal to 2m plus n for the tilted 2 torus. So thus the L minus n is even for the tilted tori. The homology cycles for a stack A of NAD6 branes along the cycle n comma L and their omega R images with the cycles n comma minus L are respectively given as the following equations, where beta is 0 and 1 for the rectangular or the tilted case. Here I have given the homology 3 cycles read by the 4 O6 planes and the corresponding definitions of the intersection numbers. So our orientifold planes and the model building requires certain constraints. One of the important constraints is the Tadpole cancellation condition, which is basically a Gauss's law in the compact space, which implies that the sum of D brane and the cross cap RR charges must vanish. So the Tadpole constraints is sufficient to cancel the SUN cubic non-abelian anomaly, while U1 mixed gauge and gravitational anomaly or SUN squared times U1 gauge anomaly can be cancelled by the Green-Schwarz mechanism, which is mediated by the untwisted or Ramun-Ramun fields. The cancellation of Ramun-Ramun Tadpoles requires introducing a number of orientifold planes, also called the filler branes, that trivially satisfy the 4-dimensional n equal to 1 SUSY conditions and belongs to the hidden sector of the, in our cases, it is the unitary symplectic group. We define the following convenient products of wrapping numbers, which using those we can write the no Tadpole condition as a simple following equation, where 2n superscript I is the number of filler branes wrapping along the IF06 plane. So for the supersymmetry conditions after compactification to 4 dimensions, preserving the n equal to 1 SUSY conditions restricts the rotation angle of any D6 plane with respect to the orientifold plane to be an element of SU3. That is the sum of the angles theta 1 A plus theta 2. These 1, 2, 3 are the corresponding tori. So the sum of all these angles should be 0 mod 2 pi. And theta is defined by the inverse tangent, and chi are the complex structure moduli for any of the two torus. So n equal to 1 SUSY conditions imply the following constraints. Here I have written x a equal to lambda, which is just a reparameterization, and similarly xb and xc. Here I gave the general spectrum for the intersecting D6 planes at generic angles, where m is the multiplicity and as and a denote respectively the symmetric and the anti-symmetric representations of unity n over 2. To have the three families of standard model fermions, we need one torus to be tilted, which is chosen to be the third torus in our case. Here we study the phenomenology of a newly found model. Before our work, several models were already constructed, but they were up to the wrapping number 3. But in 2019, our research group constructed a higher wrapping number model, having one wrapping number equal to 5. So we are going to discuss that model. The model exhibits approximate gauge coupling unification with 3 generations of chiral fermions together, besides the hidden sector with the gauge group, the 2 gauge groups, the product a unitary symplectic of 2. Placing the A prime, B, and C stacks of D6 branes on the top of each other on the third 2 torus results in additional vector-like particles from n equal to 2 subsectors, and the anomalies from the 3 global U1s of the unitary 4, unitary 2 left, and unitary 2 right are cancelled by the Green-Schwarz mechanism, and the fields and the gauge fields of these U1s obtain massive by the linear D-wedge of couplings. Thus, the effective gauge symmetry is the Pati-Slam symmetry, SU4 color times SU2 left times SU2 right. This is the main model we are going to study. So we can see in the stack B, we have a wrapping number 5. And I have shown the 2 stack and the 3 stack, which are the orientipole filler branes. And we also have all the intersection numbers, and also have the chi moduli and the beta functions. And this is the table for the corresponding quantum numbers of the various fields. So the standard model fields, the left-handed and the right-handed particles come from the AB and the EC sector. And I have stressed the exotic particles, but in the paper we have also listed some of the exotics that come from, for example, this intersection of B with the 2 and B with the 3, and C with the 2 and the C with the 3, etc. So, and BC prime gives us the Higgs sector. So the Pati-Slam gauge group is Higgs down to the standard model gauge group by assigning webs to the adjoint scalars, which arise as open string moduli associated to the stacks E and C. So, and moreover, the U1 I3R times U1 B minus L gauge symmetry may be broken down to the U1 hypercharge by giving webs to the vector-like particles with the quantum numbers 1 half minus 1 and 1 minus half 1 under the SU3 color times SU2 left times U1 I3R times U1 B minus L gauge symmetry from the A2 C1 prime intersections. This brane splitting results in standard model quarks and leptons as follows, and the additional exotic particles must be made super heavy to ensure gauge coupling unification at the gut scale. And we have the following 3-point Yukawa couplings for the quarks and the charged leptons, which can be read from the following superpotential. The n equal to 1 supergravity action is encoded by the 3 functions, namely the gauge kinetic function, the Kähler potential, and the superpotential. Each of these functions in turn depend on dilaton S, complex P, and Kähler U moduli. Complex structure moduli U can be obtained from the SUSY conditions by the following formula. And the uppercase moduli in string theory basis can be transformed into the lowercase STU moduli in the field theory basis by the following relations. where 5 holds the 4D dilaton, which is related to the supercapping moduli by the following relation. Inverting the above formulas, we can solve for the U moduli in string theory basis in terms of the field theory S and U, and the holomorphic gauge kinetic function for any D6 brane stack for the X. Wrapping a calibrated 3 cycle can be given by the following equation, where the integral involving 3 omega 3 is given by this. It can then be shown that fx can be written in terms of the wrapping numbers and the U and S moduli, where the factor kappa x is related to the difference between the gauge couplings of unitary n and the symplectic 2n and the orthogonal 2n. So kappa is 1 for the unitary group and kappa is 2 for the orthogonal or the symplectic group. The standard model hypercharge and the holomorphic gauge kinetic functions are both linear combinations of several stacks with the similar proportion. The Kähler potential to the second order for the moduli M and open string matter field Ci and C theta is given by the following relation, where Ci correspond to the D brane positions and Wilson lines moduli arising from strings having both ends on the same stack, while C theta correspond to strings stretching between different stacks comprising 1/4 BPS branes. The untwisted modular fields are not present in the MSSM and must become heavy by higher dimensional operators. So we are only concerned with the first term and the third term. The Kähler metric for the twisted moduli between the stacks X and Y in the type 2 theory has following two cases. These have already been computed in the reference papers. So we have these two cases for different signs of the angles theta. The Kähler metric for the branes parallel to at least one torus, which gave rise to non-chiral matter in bifundamental representation, like the Higgs doublet, is given by the following equation, and the superpotential is given as follows. The F-term pre-level scalar potential can then be written by using the standard formula, where Fm, these are the basic definitions. Gm is the derivative of G, and Kmn is the Kähler metric, and Kmn is its inverse, and the auxiliary fields Fm are given by this. Thus the supersymmetry is broken through F terms from some of the hidden sector fields M acquiring the webs, thereby generating soft terms in the observable sector. And Gravitino gets massive by absorbing Goldstino by the super Higgs mechanism. So in the auxiliary field formula, e to the g over 2 is basically the mass of the Gravitino. The normalized soft parameters, namely the Gaugino mass, squared scalar mass, and trilinear parameters are given by the following formulas. Although it appears that soft terms may depend on the Yukawa couplings through the superpotential, however, they are not the physical Yukawa couplings, which exponentially depend on the worldsheet area. Both are related by the following relation. To calculate the soft terms, we ignore the cosmological constant V naught and introduce the following webs for the auxiliary fields for the S, P, and U moduli. So these are our parameterizations, where gammas denote the CP violating phases of the moduli. C square is some constant related to the cosmological constant, and the Gravitino mass. Thetas are the Goldstino angles, which determine the degree to which the SUSY is being dominated by any of the dilaton, complex structure moduli, and the Kähler moduli. And all these different moduli are constrained by the following relation. Unlike the S or U moduli dominant SUSY breaking, the T moduli dominant SUSY breaking depends on the physical Yukawa couplings through the area of triangles. Therefore, we shall only concentrate on the U and the S moduli SUSY breaking with dilaton non-zero. So this is the most general case. In the paper, we have also discussed just the U moduli dominated SUSY breaking without the dilaton S. Using above parameterization, the soft parameters are given by the following formulas. So now we have the following simple equations in terms of the moduli and the wrapping numbers. So these Mx are the Gaugino mass parameters, This is the Bino mass parameter, the trilinear coupling, the squarks and the leptons mass squared, and the Higgs mass. And this is our final result for the soft terms from SUSY breaking with the M1, the Bino mass, and M2, M3 masses, and the trilinear coupling, and the left and right-handed superparticle masses in terms of Grappino mass and the various Goldstino angles. Now I discuss the Yukawa couplings. Before that, I represent our model in terms of um, configuration of various D planes. This is called the Yukawa textures. So we can see that the first torus is where all the intersections are lying. The second and the third tori are very simple. The third torus is tilted. The fermion mass hierarchies result from the intersection of the first two torus. So so the case is so in our case, if we only calculate the first the Yukawa coupling from the first torus, that is sufficient for us. So Yukawa couplings rise from open string world sheet instantons that connect three D plane intersections. This is the general formula, and for our case, for the first torus, we can take phi to be 0, and kappa we will take to be real, and it will just be some number. And the mass matrices from the 3-point functions, here we compute the intersection numbers. In the original table, we have given the total intersection number, but here we need to compute the intersection numbers or individual two tori. So on the first torus, we can see the intersection numbers are 3, 9, and 3. So they are not co-prime. So we must calculate the greatest common divisor, which is 3. So the corresponding formula for the delta, phi, and kappa are the following, where I, J, and K respectively index the left-handed fermions, the right-handed fermions, and the Higgs fields. So K goes from 0 to 8, which means that we have 9 Higgs from the BC sector. I have to point out that in the MSSM, the 2 Higgs will be the linear combination of these 9 Higgs. When we see the various forms of the mass matrices, we can find by taking various shifts in the equation of delta, the last term S1 over 3, we can take various shift values. For example, for the shift S equal to 0 or minus I or minus K, we have a general structure given by M subscript minus I. And this is a very nice mass matrix, which is rank 3. And for S equal to minus J over 3, we have another mass matrix, but here we have a rank problem. So it cannot be used to fit the various masses of the fermions. So we will just take the first case, and we will choose S equal to minus I. And VI are the corresponding webs, and A, B, C, D, E, F, G, P, and Q are the theta functions, Jacobi theta functions. We choose the case S equal to minus I for the mass matrices of up quarks, down quarks, and charged leptons. Notice that the two light Higgs mass eigenstates will arise from the linear combination of the webs of the 9 Higgs fields present in the model. And after taking the S equal to minus I case, we found that we can obtain an exact fitting by expanding the 9 up type Higgs webs and the 9 down type Higgs webs respectively for the up type quarks and for the down type quarks. So here we have set the Kähler modulus on the first two torus defined in kappa equal to 45 and evaluate the coupling functions by setting geometric brane positions as epsilon u equal to 0 and epsilon d equal to 2 over 9, which yields in an exact fitting for the following values of vacuum expectation values. So these are the webs of the 9 Higgses, ups and downs, which we can use to fit the up quarks and the down quarks, including their mixings. The only since everything is we have already expanded all our freedom, like we have assigned all the values of all the, we have assigned all the webs. We have very little freedom left for the for fitting the charged leptons. So the nearest match for nearest match for the charged leptons is obtained for epsilon equal to 0.2, approximately 0.2. So in this log plot, I have shown that this is a plot where if we draw a vertical line, we will get 3 points corresponding to the blue curve, the green curve, and the red curve, which will give us some value for the tau mass, muon mass, and the electron mass. So at around 0.2, we see that the red touches the dashed red line, and blue touching the blue dashed line, which is the reference values, but the green and the red, they are not exactly touching. So we do not have the exact fitting. The eigenvalues are such that the tau mass is fitted exactly, while the muon mass comes out to be only 37%, while the electron is about 2.45 times heavier. So since these results are only at the free level, there could be indeed other corrections, such as those coming from higher dimensional operators, which may contribute to most greatly to the electron and muon masses, since they are lighter. So then we can add the contribution from 4-point functions. For example, we can take 4-point interactions of the following form with AB, phi AB, CA, phi P prime C, BB prime, and phi AB, phi CA, phi CC prime, phi BC prime. So in the paper, we have discussed both types of interactions, but here we will I will just discuss the results. Where phi's are the chiral superfields at the intersections between stack X and Y D6 planes. There is a more intuitive way to calculate the area for these 4-sided polygons, since we know that quadrilateral can always be taken as the difference between two similar triangles. So to compute the 4-point functions, we can use we can just use the similar techniques as we use for the 3-point functions, because in the 3-point functions we were calculating the area of triangles. So a quadrilateral can all since a quadrilateral can always be taken as the difference between two similar triangles, therefore we can employ the similar technique, so our calculations will be simpler. Since we've already fitted the up-type quarks matrix MCU exactly, so its 4-point correction should be 0, which is true by setting all up-type webs U and W to be 0. Therefore, we are essentially concerned with fitting charged leptons in such a way that corresponding corrections for the down-type quarks remain negligible. The desired solution can be readily obtained by setting epsilon 4 equal to 0 and epsilon 4d equal to 1/20 with specific webs given in the paper, which exactly reproduces the correct masses of all 3 charged leptons. So I conclude that we have studied the phenomenology of a new class of supersymmetric Patislam intersecting D6 brane model on a E6 over Z2 times Z2 orientifold in type 2 string theory. The defining characteristic of this new class is that one of the wrapping numbers is 5 and the model exhibits approximate gauge coupling unification. We have discussed the standard model fermion masses and mixings, and SUSY breaking soft terms in the U moduli dominated case and the U moduli dominant case, together with the S moduli turned on, where the soft terms remain independent of the Yukawa couplings and the Wilson lines. The results depend on the brane wrapping numbers as well as SUSY breaking parameters. Although we are able to reproduce the extrapolated gut scale mass hierarchies and mixings of the standard model fermions in our intersecting brane model exactly, However, several issues remain to be addressed. The values of various couplings and other parameters are not determined uniquely within the model and are rather put by hand. So all such parameters are the functions of open and closed string moduli. For instance, Yukawa couplings depend on the geometric position of the stacks of branes and the Kähler moduli. And once we fix these moduli, the only freedom left is the Higgs sector, that is finding a specific linear combination of 9 pairs of Higgs states, which may be fine-tuned to yield the two Higgs eigenstates H up and H down of the MSSM. So fixing the brane positions is thus equivalent to fixing the open string moduli. Unless these open string moduli are fixed, the low energy spectrum will contain non-chiral open string states associated to the brane positions and the Wilson lines. We do not see such scalar particles in nature. Luckily so, otherwise they will also spoil the gauge coupling unification in the MSSM. Therefore, it is tempting to eliminate such non-chiral fields by considering intersecting D-brane models wrapping on rigid cycles. In the case of type 2A compactifications, T6 over G2 times G2 prime is the only known toroidal background possessing such rigid cycles. So this is tempting that we may explore this in a future study. So that concludes my talk. Thanks.
Okay, thank you very much, Mudassar. So, are there questions from the audience? Let's see.
Maybe I can ask something, Irene?
Yes, please. Go ahead.
Yes. So I was wondering what is so interesting about this this model where the wrapping number is so high? Like, why do you want it to be 5 or larger?
Well, I'm very new in the field, but actually my professor, Professor Tianjun Lee, had written a paper in 2007, and they had this even in, I think, 2004 or 2005. And they had found models up to the wrapping number 3. And they had such certain algorithms. So they thought maybe higher wrapping numbers is interesting, but they were not, it was not easy to find such a model. So in 2019, one of my collaborators, using some machine learning techniques, he actually solved the coupled equations, because we have the constraints of Tadpoles and the n equal to 1 SUSY conditions. So we have to solve these coupled equations. So it is very difficult in general to couple to solve those coupled equations. Instead, there is another way. Another way is we just put in random numbers and solve for each, check each model whether it satisfies the conditions or not. So they were able to find only one model having a wrapping number of 5. And there was another model, but they were T-dual to each other. So in our paper, I think it is in 2019, model 16 and model 18. So both are just T-dual. I have taken model 16 to be precise. And like it is in the previous study, for example, the best model was up to wrapping number 3. And they had exact gauge coupling unification in their model. But in our model, we have approximate gauge coupling unification. And in the up to wrapping number 3, they were not able to fit the masses. They were just not able to. But in the wrapping number 5, because the number of Higgs are more, maybe this is the reason, because we have 9 Higgs, and so maybe we have a little more freedom. However, it is not very general that if you have more Higgs, you have more freedom. No, maybe there is some sweet spot. Maybe if you have 4 Higgs, because previously they had only 3 Higgs. So maybe you have 3 to 5 or something around this range, that you have a little more freedom, because the matrix structure is very constrained. So
okay, maybe we are running out of time, so
right.
let me ask, is there any other very quick question? Otherwise, maybe we should thank. Yeah, I don't see any. So let's thank Mudassar for the nice talk. Thank you for joining this seminar series.
Thank you very much.
Thank you everyone for joining and hope to see you next week.